All right. So today we're talking about algorithms and analysis. So to get us started, I have some critical questions for you. I'm going to put you into groups, and I would like you to first write the steps needed on the board to accomplish these tasks. So the first step is, what do I need to do to make spaghetti? The second task is, what do I need to do to alphabetize a list of 5 books? So currently the first letter of them is in the order URKDA, which is not alphabetized. And then what is the step to do laundry? Let's put you in groups. All right, so we're going to go back and forth with recording and stuff today because it's going to be super fun. All right, so what we've looked at are algorithms. An algorithm is a procedure to accomplish a specific task. It has some input and it has some output. Sometimes there's no input and it just does something and gives you an output. Sometimes there's no output and so it just does something. So we can draw it kind of like here's our input and then here's our output. And there we go. So an example of an algorithm is I'm going to go bake chocolate chip cookies. I have ingredients, that's my input. I go and bake, combine ingredients, put it in the oven, and my output is my delicious cookies. I could draw things on a screen. So I could say, draw this line. I have a program that I tried to get working, but it didn't work. So I have this program where I drew lines and said they were bricks. And so I drew like one line and another and another. And each of those are steps to accomplish the ultimate goal of I'm drawing a brick wall. Reading in a file is also an algorithm. Also, for something like for my research, I compute pairs of angles of triangles of these triangles are at this angle, and I do that for each pair in the file. Those are all algorithms. So now I've got a question for you. So let's consider a program has 200 instructions, so maybe 200 lines of code. And if I've got some lists of computers, so the UC Berkeley supercomputer, the 15-year-old PC that I pulled out from the back of my closet, and my new laptop. And each of those has a processing speed. And so the supercomputer can process 2 million things per second. My really old PC can only do 10, but my new laptop can do about 1,000. So in your groups, maybe use the whiteboard. How long will for each of these computers, how long will it take to complete? Okay, so yeah, so the supercomputer can do things very quickly. My terrible computer can do things very slowly, and my new computer can do things decently. So I've got a question for you. If this is all running the same program, is seconds a good way to measure the execution of an algorithm? Turn to your neighbor, talk about it. Why are you pro or con?
It's not across, whatever's. Very little sentence.
Maybe you want smaller sentence.
It's also like.
Yeah.
Powerful and like that.
Entry step forward.
Okay. Any arguments pro?
Get the thing done pretty quickly, get the result faster.
Yeah, if it's fast, then it's fine. Pro would be also like sometimes the computer you run things on actually matters. And so if you know the computer is going to be constant, then seconds is fine. So depends on computer. The con is also depends on computer because like saying this program takes 20 seconds, like I run some fairly intensive things. If something takes 20 seconds and it's fairly simple, then I'm like, okay, something's wrong here. But if something takes 20 seconds on the laptop stuck in my closet, maybe that's reasonable for it. Other things for con, why wouldn't we want to use seconds? Yeah.
It would become like really small when it's if your computer is done. Like you know, so many decimals.
Yeah, so it's like super tiny numbers, then what's the point? Uh, okay, so as a whole, computer scientists have decided that seconds are not the way that we want to communicate this information about how fast an algorithm is. So we're going to make up a machine and we're going to come up with a new way to measure this. We're going to call this the random access machine. And this gives us a model where we're going to say every simple operation, so that's addition, subtraction, multiplication, assignment, if statements, computing any conditionals, calling a function, all those sorts of things takes one time step. Time step is in quotes because in actuality, it could take my super old PC forever to do one thing, but it can take the supercomputer negligible time to do things. So we're going to say it takes one time step. And we'll also assume that memory access takes one time step. That's not necessarily always true. So if you go and take an operating systems class, you'll learn about the cache and the disk. So we're not going to care about that. We're just going to assume if we need it, we can access it in one time unit. That being said, loops or subroutines, function calls, like not necessarily just so calling the function of like, let's call the function hello. I have called the function, but actually doing the stuff in the function hello is a different matter entirely. Because hello could have like 300 for loops all nested inside of each other. And I don't want to assume that that takes constant time, right? So actually doing the subroutine is a different matter. Actually, the loops is a different matter. So in this model, our goal is to count how many steps get taken, how many quote unquote, how much quote unquote time is needed to complete all of our operations. In this way, we can look at the code itself. And when we look at the code itself, that means we're machine independent and language independent. So we can look at any language and say, I can read these steps. This is 10 steps. Doesn't matter what language I wrote it in. Doesn't matter what machine I run it on. It still takes 10 steps. Okay, I have an activity for you and your groups called Race to Trace, which is I'm going to give you a snippet. Let me show you what the first one looks like. So it's a snippet of code. It starts easy, then they get hard. I'm going to give you 1 minute to stare at it. So for the first one, you're going to be staring at it for a long time. And then 2 minutes to talk about it in your groups. And then once that's done, I'm going to want you to call out how many operations, like give me a number of operations get completed for each snippet of code. So let's start with maybe 30 seconds for the first one, because it's not that complicated. So 30 seconds. All right. Stare at it and count. All right. Turn to your group. What number did you get?
Yeah.
Oh, wait, I was. I was calculating all the junk stuff on there. Oh,
I just counted a lot.
This is the number.
Oh, you mean?
I'm saying eight.
I do it big.
The $5. Zero. Then you have five.
Oh, we're adding that also pulling.
Yeah, 'cause you're pulling out.
So that'd be two.
All right. What'd you get?
Eight.
8. Hooray. Why?
8 lines.
There's 8 lines. This is correct. That will not always be true. Where the number of lines does not always correlate with the number of instructions that get completed. But yeah, so there's 8 operations. So that's 1, 2, 3, 4, 5, 6, 7, 8. Hooray. All right. Number 2. Let me start my timer. I'll give you 30 seconds again.
Oh,
Yeah, so is it like?
or actually, like 1, 2, 3, 4, 5, 6, 7. Okay, we're at 8.
Wait, is it right again?
That's true, that's fine.
What?
We're
Yeah.
wrong.
This is high.
Yeah.
Yeah, so this is language independent. So you will see languages other than Java here.
Okay.
This is the one
Okay.
that's for 8.
So I will tell you the answer is not 5.
8.
It's 8. Why?
It just did exactly what you did in the last
Well,
one.
I think.
I feel like.
Do a loop for 5 of them.
And then.
Instead of
every time
infinity,
you-
then it's all-
And then. But.
So there's the first 2, and then there's 4, and then you add, and then you run through it 5 times, so that's 8, and then that adds to it.
But that one instruction happens.
Okay,
Well, the total.
So- there's 1. There's another. There's another. How many times do we do that? And then
8.
that's 1. And so we have 5 times 1 plus 3. That's 1. Wait, 5 times 1 plus 3, which is 8.
Huh?
Unless I've done my math.
What about, I thought,
Not half. Like 4 after name doesn't.
Right, so the for loop, so that's where the for loop comes in, is in the multiplication. So the for loop is like, we're gonna do this a certain amount of times. And so we ask 1, 2, 3, 4, 5. We have to do it 5 times. So we do one thing, which is the total plus equals X. We do that one thing 5 times. Again, so yeah, so it's not about like the lines of code, but it's like, what are we doing? Okay. This happens to be in C++. I'm gonna give you,
It's me.
giving you 2 minutes
Wait.
to fight about this in your group. Does declaring count? No. Only if we decided to go, if we decided to call main, that would count as one.
They're fine.
So it's one, that's just a bit.
So
Oh,
what?
wait,
If stream is input stream,
fall through.
input file stream.
Yeah.
Streamline is two. Well, yeah, yeah. And then the Y.
I'm gonna go for eight, yeah.
Oh, yeah, Mike.
Then the-
Follow through.
Just those things, you know, it's not
Wait, what if it's false?
Well, while true just means that it's until you really want it. So there's like while true means it's like, it's off.
So it goes like, then it goes in a line of four lines, so three times.
C out is C++'s way to print something.
Plus that.
Streamline.
What is count line and end?
C out is output printing. End L is end line. And so this is saying I'm printing this line and ending it with a new line.
Oh, the data.
So then that would
So
be
it's
four,
in the 4 times. So 1, 2,
six, seven,
8.
eight.
Yeah. Just return count. I'm just kids just screen. I didn't count this one out. But. Fine. What's this?
All right. Have we reached a consensus? All right. What is your guess? 8. I have 13.
Oh.
Let's see. Okay. So that's 1. That's 1. So yeah, so I'm willing to flub for like 1 or 2. But so okay, that's 1. That's also 1. That's 1. So like there we go. So this is the file in question. How many lines does the file have? 4. So my while happens 4 times. And so this is also a bit of a question, like, because I don't know exactly what getLine does. If we assume it just takes constant time, then we would say that the if statement just takes 1 time step. So we have 1 plus 1 plus 4 times, so we're going to compute that and assume that we're not done yet. And then we print things. So 1 plus 1. We do 2 things until the last time around. And that's the break. Takes us out of the loop. And then we close the file and return 0. And so that is 2 plus 4 times 2, which is 8, plus 3.
This is the time, and so this is the and the or this, yeah.
And so 10 plus 3 is 13. So it's not 8. Is that clear? All right. We haven't talked about this yet. We will talk about this on Thursday. This is your chance to puzzle about this. So this is like 1 file of code, and I would like to run it.
Signatures.
Well, we're not,
I'm gonna start my timer.
Yeah, this we're not.
so it isn't.
Okay, so you want to do that.
If n is.
Factorial.
Of four. Less
Well,
than
the
one.
thing- You're only gonna return one of those. So
Return what?
count one of them.
Yeah.
It'll either return one of those.
Back.
It's very one time one.
Just gonna do the if again.
3.
This engine.
Three.
N times factorial.
Wait.
N minus one,
That's a
those,
point, then
how that's
don't bring anything from the sign.
like N minus one.
Oh, no,
N
this is
times
four.
one, and then everything is another one, and then the term is a third
But
one.
I'm not sure if the return.
4 times.
Yeah, return time. I guess we'll just count the other.
It's only been 4.
You count
Return 4.
Yeah.
it.
4 multiplications and then printing it, that's 5. Or say 5.
N times. And then N minus. And I guess count the other. And then, so 6.
All right. Are we ready to guess?
8.
The answer is not 8.
Good guess though. I think it's 5. 6.
I think it's 20.
9.
20, again, plus or minus. Plus or minus. Okay, so
Oh, that's the end.
So I think this counts as 1. That's a function call. So I'm willing to consider combining those two. But the actual execution of the factorial function, this is what we call a recursive function, by the way. Will you do this on the final? Yes, we're going to talk about recursion next time. So this is my sneak peek for recursion. But for now, we're just learning about operations. So the conditional, that's 1. The return is 1. And then here's where I will accept 2 or 3 or maybe 4 if you want to get super into it. Like the return could be 1, multiplication could be 1, the function call can be 1. Maybe. Again, maybe I could buy that. I can hear arguments. I will not consider that. Right. So okay, so we could consider that. We could consider that. So those are all the operations, except factorial of n minus 1 is doing factorial all over again. So let's think, how many times does a factorial? So we've got a number 4 here. So we're doing this, we're doing something 4 times. And then we've got 1 for the if, plus 1 for the return, maybe plus 1 for the multiplication, plus something for the call. So and so this is recursive, where we're gonna write it as an equation T of something, where we have 1 plus 1 for these two, the print and function call, plus, and then inside the function we have 1 for the if, and then 1 for the return, 1 for the multiplication, plus T of 3. Okay, we're gonna look more at this later. I've got another one for you. This one is in Ruby. It's another programming language.
Whoa. Pretty fantastic.
What does end mean?
Is it like the end of a loop? It's like.
Yep. So the if statement starts here and it ends here. The for loop starts here and it ends here. The for loop starts here and it ends here. The function starts here and it ends here.
I don't like those ones discussed.
It's just a different style of programming.
I think I think this is what programming is.
Yeah.
One.
That's what the kid is.
For I and zero dot dot dot.
How many instructions get completed? It's just a for loop. We know how for loops work.
You know the answers.
I do, but I would like you to come up with the answers as well.
Yeah, like,
It's like 35, isn't it?
for J and zero dot dot dot, would for I and
And
It's like up there. It's like, I know it's like,
Yeah, I got like 40.
See, I'm close enough, that's close enough.
But how did you get 35?
I just threw it up there. And it's stuck.
No.
It's like spaghetti.
So that it's the array error.
You know, what's the common result?
That's a great
But I'm
question.
saying, so like,
Did they make this programming language?
a for loop, is not a for loop, is like.
Say that again?
Did they make this programming language to like?
For I,
Two.
zero.
No, but there are programming languages like that. I think there's the Moo programming language.
Wait, how many more did you have? Like, how many more? Like,
There's 7 total.
how many? Oh, is there 7 total?
Say that again?
Oh, I should. I hope not. You know, I think I have my new answer. It's 40.
However, did you get that?
So basically, you keep counting 40, right? And then
What
you
array
count
is
it,
that?
and that's
One
8
eight.
times.
It might be 8.
You get.
No, is the array, setting the array? Might be 9,
Yeah.
10.
All right.
I'm saying 10.
Oh, because you get 35 before the stuff, and then like the array is like 4. No, it's
You
not.
add 3 and then 2 also.
Or, yeah. See, this is 0, 2. I should just.
So
Yeah.
the outer for loop does something n times.
Who's to say what n is?
Yeah, I'm at 10.
All right, there.
That's to say what n is.
Oh, 10 plus n. 1.
How many times does the inner for loop happen?
The inner loop happens 2 times.
Oh, the inner one.
5 might be 10 times.
What's
Yeah, so we're looking at this loop, and so we've got 0 to n minus I minus 1.
What?
Where does I range?
What class are we in? What's the name of this class?
Where does I start?
I'm so sorry. I got it all tape.
It starts at 0.
I starts at 0.
Can you save it?
No, because we're in a for loop. So n minus 0 minus 1 is
3.
n minus 1, which when n is 4, that's 3. What's the biggest value I can have?
No,
Oh, no.
minus 1, so, wait.
N minus 0 minus
Wait, is it
5
like, I
equals
swear the
4.
last one is like, it's 1 less.
Think so.
Okay.
I think so. That's standard.
Is it n minus 1, that is 1 minus 1 again? Then
Right. So, okay.
2?
Yeah. So that inner loop happens at most n minus 1 times. Because we're starting 1 off. We're starting at n minus 1. And then go all the way to the end.
It's not.
This won't be on the final, right?
No, it will be.
No.
Ruby itself will not be on the final, but being able to determine how many instructions something has,
Blue gonna be on the final?
no.
Yeah.
Okay, and then inside that, we have 1, and then I can argue this either counts as 2 instructions or 1, because it's doing this weird sort of double assignments. This, you can do this in Python, by the way, where if you have a function that returns 2 things, you can catch like the first one and the second one. It's super useful. Java doesn't let us do that, which is maybe good, but sometimes frustrating. So this is either 1 or 2. I'll say 2. So how many times did this happen? So we've got 3 plus 1, that's that guy, plus n something n minus 1, and then something 3. What happens between n and n minus 1? Okay, so, all right, let me erase that. Okay, our outer for loop goes from 0 up to n. We've defined n to be the length of the array that we're given. So this loop happens n times, right? Which is 4. The inner loop, if we put I as 0, that gives us n minus 1. So that very first time we go through the inner loop, we're doing something n minus 1 times. Right? So if we put I as 0 here, that would just be n minus 1. Right, and that it'll get smaller as we go. So first, if we are doing it 3 times, the next time we go through, we're doing it twice. The next time we go through, we're doing it once. And then in each loop, so like within that, we're doing some comparison and we're doing some swapping. Some operation. I don't actually care what it is. It just is an operation. So we're doing something n times. I've got 3 numbers here that will finish. Do I multiply or add them? Multiply. I know that was a shot in the dark, but it is correct because we're in a for loop. So if we go back to here, we did that one thing 5 times because we're in a for loop. We did these 2 things, the conditional and the printing. We did those 2 things 4 times because we're in a loop. We're going to do these 3 things, or 2 things, n minus 1 times, and again, n times, because we're in nested for loops. Question?
Out with the if statement, even if the if statement doesn't execute, or like if it's false.
Yes, because even if the result is false, we still did that comparison. A comparison was made. We just didn't enter the if statement.
Do we do what's like in like the A did that part? Do we count that part too? The 2?
This,
Yeah, because like if the if statement is false, then do we still count that part?
oh, good point.
Like if
Yeah, so I'm going to, because I don't know what sort of conditions I'm given for this array. And so I'm gonna assume the worst case and assume that I'm doing this every single time. Again, I don't necessarily care exactly what I am doing. I am just counting the operations at this point. So we get to some equation like T of n is equal to 4 plus n times n minus 1 times 3 plus 1, which is 4 plus 4 times 3 times 3 plus 1, which is, I said 40. Congratulations.
Yeah.
Okay. All right, this one is hard.
Is it over or under 50?
It's gotta be over 40.
That's what I'm thinking.
Yeah.
It's been increasing like, it's been steadily increasing.
Most that I can fit.
You're talking about
What's 2 to the 6? 36, so I think it's under 40.
Under 40?
Yeah,
You get a calculator out.
because that was because I can't do math in my head.
That's one.
Yeah.
Turn N to church it, 3, 4,
big.
5, 6, 7.
What? 64.
That's a 7.
Okay, so it is bigger
It's
than
big,
40.
It does things like 2 to the 6 times 2 to the 6. 2 to the 6.
Okay, so I've in fact given you the answer, which is 2 to the 6th plus
Plus 7.
some things plus 7. Great.
Is it not?
Why the 7?
If n is less than 1, return n 2, and then div n minus 1, 3, and then plus 4, 5.
In return?
Return 6, and then last print 7, and then plus the fifth 2 to 6.
Okay. I do not buy that these are 1s. Everything else I'm okay with.
You do math.
Well, so, okay. Okay. I can buy that.
Okay.
I can buy that.
Okay, cool.
I can buy the 7 part. The important part is the 2 to the 6th. So let's say I'm doing, so if I write my equation of the number of time steps, t for time, t of 6 is going to call t of 6 minus 1, which is 5, plus t of 6 minus 2, which is 4. T of 5 is going to call t of 5 minus 1, which is 4, plus t of 5 minus 2, which is 3. And there's an extra t of 4. And this keeps on going. So until we get to t of 1, it'll keep expanding. And so the hand wavy explanation for this is at each step, we call 2 things. So at each step, t of n, we call t of n minus 1 plus t of n minus 2 plus, I don't know, maybe 7, right? And so at each step, we make this call twice. So there's 2 calls, and then 2 calls, and then 2 calls, and then 2 calls. And those all get multiplied together. And so for that reason, we have 2 to the n. And so since n is 6 in this case, we get 2 to the 6th, which is 64. Plus some number of other things. Okay. How about this one?
Got it. That's what she's saying. Put that in terms of- And then it returns. Let's see.
Okay. Do we have a guess of a number? 5 or 8? Other guesses? Yeah, so we're in that range. So I said 6, which is print, and then the function call, which calls message equals greet. And so the equals, that's the assignment, that's one operation. Greet is another operation, which just returns something. And then we return this message. So that's is for a sum of 1, 2, 3, 4, 5, 6. So depending on what you believe, maybe that counts as another one. I don't know. Again, plus or minus some number, I don't really care. All right. So in general, as a reflection, how did we calculate these numbers? Counting, yes. Turn to your group and reflect. How do you compute for something like that initial for loop or the double for loops? Yes, we're tracing. All right, so we have this relationship between addition or multiplication, right? So typically our statements that just stand by themselves, those are just ones, and then we add all the ones together. But then if we're doing something some number of times, we're multiplying. So we're doing that however many times we said we would do it. And so that's when we multiply. Okay, so now we're going to start to consider general functions. So in the previous examples, we had some sort of fixed input. So like a list of 5 numbers or like a list of 5 books. And so we've got one solution over there of like you switch the first and the last, and then you switch the second and the second to last. And that's perfectly fine for a list of 5 books. But now we're going to start to transition to general functions. So where we want to alphabetize a list of n books, and it's currently completely reversed. How do we do something like that? Talk with your groups. How did your approach work for this general case?
And what if there's 20 books and there's one named like B, C, like sure, but that makes sense. It's all letters.
Teacher, they're just reversed.
Now we're this kid.
Because they're all square.
All right, so when we start to consider what algorithm do we need to solve this sort of problem, you're probably going to be given some general question of, I have some number of books. I don't know how many books I have. I don't necessarily want to specify I have 10 books or 15 books or 20,000 books. I don't want to specify. I'm just going to say I have n books. So we have to consider not just how do we do this in any particular instance, we have to generalize it. Okay, so we're going to go through some of the examples, some of them we've already done so far. where I want to come up with an equation, and not in terms of the actual numbers, but in terms of n, where we're going to say n is the size of our input. And that is standard across any computer science course you would take. N is the size of our input. And so we're going to count the number of operations that are taken. We're going to write it as an equation. So for example, if I have a nested for loop and I do those things and I have 3 sets of nested for loops, that would give me 3n squared. And then if I have 100 single for loops, that's 100. And then maybe I have 6 other things. I write those all into an equation, and I get f of n is equal to 3n squared plus 100n plus 6. F of n or t of n, where t is time, are frequently used. The name of the function doesn't matter. The content of the function matters. Okay, so what should this be? So that we know that this takes 8 steps for an array of 5 things. For an array of n things, how many steps does this take? N plus 3. So this happens n times, and we do one thing n times, plus, if we count assignment, there's 3 extra things. And so we say t of n is equal to n plus 3. That's my equation. Great. How about this one? First of all, what's my input? Okay, so the file's my input. And so it currently has 4 lines. So we're going to consider that it has n lines. We're generalizing the size of this file. So again, I've got 1, 2, 3, 4 things just hanging around there. And the while loop happens n times. 2 times n.
And then plus the
Plus 1.
plus 4.
Why do you have 2 times n?
Plus the is and the,
You're right. 2 times n plus
yeah.
4 or 5. That number isn't super important. But yeah, that's the idea. Yeah, all my solutions, I say 2n plus 5. Right? So we're still computing it the same way. We're just changing the size of our input to n as opposed to a specific number. This one, everyone's favorite, we've already kind of done, where we do the outer loop n times, we do the inner loop at most n minus 1 times, and then we do that thing twice. Multiply it all together, add some number of things at the ends, and that's our equation. So instead of an array of length 4, we're looking at an array of length n. So we have n times n minus 1 times 2, plus whatever. Okay, so once we have this equation, great. This allows us to generalize how will our algorithm work under any possible circumstances. So I can have this function that I call for however long my array is. And so that's useful for, we can write a small thing for testing to make sure it works, but then we can calculate how long would this take if my algorithm ran on a really huge data set. That's important to think about for projects that you write for industry or internships, where you can write something that doesn't take very long with a small amount of input, but could take a really long time with a large amount of input. This is a problem that we ran into in the summer research program when I was working with my student this summer, where like for a small file worked fine, but we give it something super complex and it takes like 20 minutes. And we're like, I don't want to wait 20 minutes to process a file. I want it to happen in 20 seconds. And so we have to go through, ask, what is each step doing? What is it calling? What's the complexity of that? And then we have to work our way down the rabbit hole in order to actually fix the problem. All right, so once we have this equation, we can do 3 calculations. We want to know what is the best case performance for our algorithm, what is the worst case, and what's the average case. So if you go on to take 374, we will look at best case and average case. But today we're just going to look at the worst case. And so this is considering if like the worst case happens, if every single time this if statement is triggered, what happens? And so that sort of comes in where we've got this function now, and so we can graph it, right? We've got f of n is equal to some polynomial. We can graph that. We can open up Wolfram Alpha or open up Desmos and put it in and see it. That function is going to have an upper bound and a lower bound, where it's going to have, there's some function that always does better, always does worse. Wait, nope, I flipped them. The upper bound is, since the f of n, t of n is the time that it takes for something to run, the upper bound is I can always beat that and give it more time. The lower bound is I can always undercut that. I can always do that faster. So yeah, so if you take 374, we'll talk about this. For big O, which is what we're focusing, this is worst case. So once we have an equation, that's a terrible line. Don't know that I like the way that it draws. So we have an equation, and to get the big O, the basic idea, again, this is a little hand wavy, we'll do this more in 374, is we throw away any constants, so the +6, it's out of there. We throw away any lower power terms. So 3 times n squared versus 100n, the n squared wins. That's a higher powered term. So the n is out of there. We also throw away any coefficients. So the 3, it's out of there. And that gives us big O of n squared. So here are the general categories for big O. So again, these are just equations. So we can have O of 1, which we call constant time. We can have O of log n, that's logarithmic. O of n, which is just linear. And we can graph all of these. So we can graph like y is equal to n squared. That's something we can see, and that gives us that line. In general, if we say that something is log n or O of 1 constant, great. We could probably not write a better algorithm. If we write something as n, that's pretty good. If we write n log n, yeah, it's decent. Maybe we could try and do better. Once we get into the polynomials, like n squared and more, we can have 2 to the n, that's our Fibonacci. We can have n factorial, which is just astoundingly bad. Then it gets terrible and very, very slow. I also have to tell you about logarithms. Logarithms feel kind of scary, but they're not. I'm going to tell you that logarithms happen when we divide things repeatedly. So when we divide something repeatedly, so for example, we'll see something where you can divide it, we divide it by half every time. When that happens, we have a log base 2 of something. If we divide something by 10 every time, then that gives us a log base 10. That's the general idea. All right, so I would like to know the answer to this question. Let's start with n and n squared. So if the big O of a particular algorithm is n squared, I want it to take, and it takes 2 seconds to complete the algorithm with a small amount of inputs. How long is it going to take with 1,000,000 inputs? How do you get 2,000? Okay, almost. Okay, so we've got this question on the worksheet, which we probably won't get to today. Okay, so the way that we solve a problem like this, I do not like how it erases it. Okay, so we've got 2 seconds to complete something with 1,000 inputs. There's also some overhead. So given that it takes 2 seconds to complete the algorithm with 1,000 inputs, so we're also working on a computer. So remember, now that we're in seconds, we're working with a particular computer. This particular computer has some overhead, where there's something that's going on in it that makes it like there's some scaling factor that affects it. And so with this information, we divide 2 by 1,000, and that gives us x. And then we want to know how many seconds does it take with 1,000,000 inputs. And then we plug in our 2 over 1,000, and then we get our number. What needs to change for this calculation to compute something with n squared? No. So let's look at this first one first. So let's assume we're looking at the big O of something is O of n squared. What's n? A 1,000, yeah. So repeat after me. N is the size of the input. Congratulations, that's a test question. So to change it for O of n squared, we square the size of our input. To change it for O of n cubed, it's 1,000 cubed. To change it for n log n, it would be 1,000 log 1,000. That makes sense? All right, so first we find the overhead of the machine, and then we calculate for the new input size. All right. Okay. I think I will skip this for now. I do want to tell you, we're going to talk about, so on Thursday, we're talking about recursion. Then we'll have a lab next Tuesday, and then we will talk about, or wait, no, maybe. No, hold on, let me look at the schedule. Okay, yeah, so, today we're doing Big O. Next time we're doing recursion. Then we have a recursion lab. Then we're talking about sorting. So there is a terrible algorithm. I think it's, now I erased it. Hold on. This before, Bogosort complexity. It's terrible. N times n factorial. That's bad. So, because that will scale, and like n factorial scales really quickly. Like 5 factorial is 120. I don't know the others off the top of my head, but like it's huge. And so Bogosort is a famously terrible sorting algorithm, and you have an extra credit assignment to give me an algorithm that's worse than Bogosort. So it's going to take work, and you have to convince me. Okay. Yeah, if you can come up with that, then great. There's a Wikipedia page for Bogosort, and there's a list of like, here are things worse than Bogosort. I've had a student do the algorithm where like it checks if it's sorted, and if not, it destroys the universe, which the student implemented as like the computer crashing. I've had one where like it will outlast the heat death of the universe.
Oh.
Like you got to work really hard to make something worse than Bogosort. So that's fun. Okay. In summary, we're talking about computational complexity. How good is an algorithm? The way we do that, when we have the algorithm in front of us, we count how many operations, how many steps have happened. Something helpful that you may choose if you look at it and you're like, there's one operation that is clearly important here, you can choose that. Otherwise, you can just look at all of them. The easy way to find this out, count the number of loops. Look at the arguments of the loops to make sure you're not missing anything. And then once you've got your equation, ignore the constants, round up, choose the highest term, and then you're good to go. All right, we've got 13 minutes left. So I'm gonna have you, I've got a worksheet for you, which we will almost certainly not get through. Okay. So we've got Big O worksheet. There's also the solutions, though I don't know how good they are. And so this is all practice where I would like to know more of the same, where I would like to know what's T of n, assuming n is the size of our input. In some cases, it's capital N and capital M. In some cases, it's just capital N. Some of these are tricky. So once you find that out, what's that, and then what's Big O, that's the first page. If you download it, I think that gets fixed. Where I have a bunch of equations. What's the dominant term? So for example, for this one, for the first one, what's the dominant term in that equation? 0.001 n cubed. And so this would be Big O of n cubed, because we throw away any of the other terms and we just go with that highest power. So there's those. And then I have more of those kinds of questions. So in your groups for the last 10 minutes, pull this up on Canvas, start working through it. Go for it.